Hello, welcome to Coffee Break with Microchip Technology. Coffee Break is our ongoing forum in which we discuss new and evolving technology, all in about the amount of time it takes to drink a cup of coffee. I'm your host, Eric Glatfelter. Let's say hello to our moderator, Aaliyah Fahout.
Hi Eric, and hi everyone. Thank you for joining us today. We are currently live on YouTube, Facebook, and LinkedIn, and you can participate in today's episode by leaving your questions and comments in the chat, or you can email us at livestream@microchip.com after the broadcast. If you're watching on YouTube, you can ask questions in the chat, so make sure to subscribe and click the bell so you know when we're live and when our next episode is. And on LinkedIn, you can submit your questions in the chat and subscribe to the event to get all information related to the episode. Back to you, Eric.
Thanks, Aaliyah. Our topic today is silicon carbide-based solid-state circuit breakers beyond automotive. Joining us in the studio today is Coffee Break veteran Jason Chang. Jason, you've been here a few times before. Welcome back.
Thank you. Good to be here.
All right. So we're going to talk about solid-state circuit breakers beyond automotive. Before we talk about the application space a little bit, would you remind our audience about the primary advantages of a solid-state circuit breaker versus a mechanical circuit breaker or mechanical relay?
That's a good starting point because a lot of what I'm about to say carries straight over to all the other markets that solid-state circuit breakers can play into. So let's just dive into it. Back from our season 10, episode 3, we discussed primarily five areas, main areas. One is the operating capability of the circuit breaker. You know, it uses silicon carbide MOSFET devices and silicon carbide gate drivers. As a result, is very compact, does not require all these bulky economizers and coils to both pre-charge as well as switch and de-energize the circuit breaker. So it's a very compact system and a very high-performance silicon carbide-based switch. The other one is the response time. It's very fast, so typically a traditional relay might accumulate energy to a certain point, it'll detect a fault, and it'll trip. And at that time, when it switches, there could be, potentially arc. And that arc could be, a spark that it's not good if you're in a fume or hostile, explosive environment, let's just say.
Sure.
And it could be damaging equipment. Whereas the silicon carbide switch is very low energy. Typically it switches so fast in the hundreds of microseconds versus hundreds of milliseconds that a regular switch does, so that you can detect that very low energy. So when it does switch detect a fault, there's no arcing because the let-through energy is so low compared to, it's a fraction of what you would see in a traditional relay or switch.
Okay, now let me interrupt you there. As a human being, milliseconds are pretty fast to what I can process in my brain.
Yeah.
So the difference between milliseconds and microseconds, I know what that is in mathematical terms, obviously, but can you describe for us a little bit more, how that might save your circuit in a real-world application?
Well, funny thing, the only thing that comes to mind, I'm just pulling this out of the blue, is I was swatting mosquitoes the other day. So a couple of mosquitoes on the door, I went whack, whack, whack. To me, that's probably milliseconds, because I'm very slow in trying to target with the mosquitoes on the wall.
Yeah.
And so microseconds probably just zap. I mean, it's just a blur in the eye. So that might be the difference. The blur is just instantaneously fast that, from human standpoint, we may not detect it.
Sure, okay.
All right. And then, to wrap this up, obviously this aging and wearing mechanical components, that actually leads to the potential arcing. But all these components require downtime. If they fail or they switch, you need to send somebody there to take them out. Where electronic circuit breaker is, we call it E-fuse in microchip terms, but a solid-state circuit breaker. It trips, and when it trips, it can be reset, it can be controlled remotely, and it doesn't have all the moving components, so it's actually quite reliable. You can place it in a more compact area away from a service bay, for example. So you have more flexibility in designing the circuit breaker to where you need to, rather than having to force fit it in an area where people need to access it in order to try to minimize equipment downtime.
Right, okay, so it sounds like you're gonna have a more compact design because you're limiting the coils and things like that. Yeah. And then also less likely to have to physically interact with that in a fault situation.
Right.
Okay.
And it's much faster, so it minimizes any potential downtime.
So in addition to those performance enhancements, you've got the compactness and the less interaction, if you will.
Correct, and it's quite scalable too, and we'll cover it in the next section.
Okay, okay. So we want to talk about this application space beyond automotive. Yeah. So as we get into that, could you maybe tell us about what are the system characteristics that a silicon state circuit breaker might be particularly adept for?
That's a good point. Typically, beyond e-mobility, as we call it, there's obviously higher voltages. Potentially you could scale to 1,000 to 1,500 volt voltage, the DC level, and that's typical today. The region approaching the medium voltage range, and they can go much higher than that, 2.3 kV, and well above to 10 kV in some grid applications, for example. So those are the voltage characteristics. The current-wise, in e-mobility, you're probably in a 10, 30 amp range. It's adequate because you're putting it in a car, for example.
Okay.
But beyond an automotive, you're talking about the low end, maybe 50, 100 amp on a circuit breaker switch, all the way up to potentially over 3, 4, 5 kiloamp range in massive power distribution system. Yeah. So it's quite a broad range. And as a result, silicon carbide is great for that because it has the higher thermal tolerance, the higher performance switching, and you can scale, for example, all the way from 650, 700 volts on the low end, all the way up to 3.3 kV and beyond in terms of silicon carbide solutions today. And of course, that also depends on the number of devices and the voltage, the specification of the system. So it's quite flexible there.
Okay. So with those, kind of system characteristics that would be ideal, how does that translate into the actual applications where this would be most likely to be deployed?
So let's take a look at a couple of application areas. For example, smart grid or intelligent distributed microgrid, as most trends are going toward in communities. And these are intelligent systems, typically bidirectional power flow. They're very high voltage coming from the AC line side into the communities and converting to high voltage DC to DC that you can use at the household. Throughout the area, especially in the DC part of the circuits, there needs to be protection because once a circuit blows, potentially can basically turn off power in the whole community. So
right.
So the earlier you detect that, especially with solid-state circuit breakers, then the quicker you can respond or redirect the power flow, and also protect the appliances in homes or the battery energy storage systems that are on site or off site somewhere that's storing and delivering the power flow when needed. So these circuits are very important, and potentially I believe there's an ABB industry report one time that said, utilities could save in the range of upward of hundreds of thousands of dollars of using solid-state circuit breakers because it's just their energized network is up much longer. So
okay.
That's the money they don't have to take down from servicing.
Right.
Right.
Okay.
And then, for example, another area.
Sure.
You're talking about ships and cruise liners and such. These are massive power distribution systems, and usually with multi-network, distributed network of power systems on board. If a fault is not detected early enough, potentially that could ripple through the system and trip multiple fuses and literally bring the power plant down.
Right.
Okay. Just redundancy that hopefully it doesn't happen, but potentially is there, and the solid-state circuit breaker switch fast enough so the control room can notice that and either isolate the fault or redirect the power and take some action.
Right, so I think many homeowners could relate in maybe a simple way that, one thing trips in your house and the whole panel goes down. Is
yes.
that kind of a similar?
Similar. You want to try to avoid that and try to isolate that fault maybe to
right.
a particular light fixture or something.
Right.
In home speak.
Okay.
Yeah.
Okay, great.
Right.
Okay, so, one of the other things about, this is a solid-state silicon carbide-based device, so we can integrate other functionality into devices, as the semiconductor business often does. We integrate more and more things onto one circuit. So,
yes.
what are the other kinds of functionality or some of the other features that can be integrated into these devices?
That's a great point. Before we go on to that, I actually wanted to make
sure.
a couple more points to the markets.
Sure.
I mentioned earlier the ships, like maritime vessels. A great point is industry reports actually indicated, because dollarizing it also helps our customers understand the potential savings using solid-state circuit breakers. Like in a cargo ship, for example, they might realize savings of potentially $100 to $1,000. And in cruise liners, for example, the big, massive new cruise liners, keeping power up is very important because that could be millions of dollars a year. Sure. I mean, over a 10-year period, they could save $1 million a year. So it's cumulative effect of, impact on bottom line for a lot of these businesses using solid-state circuit breakers. And the same goes for industrial, aviation, railway systems are being electrified nowadays. All the same benefits we talked about for grid applications, energy storage, maritime vessels apply there as well, with even more importance in airline and railway, for example. Many equipment is very tight spaces.
Right.
Control equipment, circuit breakers. If that circuit breaker energizes an arc, you can see the potential of bringing down even the control equipment, electronics surrounding it in a very tight environment.
Yeah.
So solid-state circuit breakers do not arc, and this is another highly added benefit to keep the system running, reliably in such tight environments.
Okay, so better uptime and reduced maintenance costs.
Absolutely.
And I would expect those maintenance costs are highly specialized.
Yes.
Okay.
Yeah.
All right. Okay, so let's talk about some of the other
networking,
features
right.
then. So again, like I said, we integrate lots of things. We meaning the semiconductor industry.
Right.
We integrate lots of things. What kinds of additional features and functions are we looking at in the solid state circuit breaker space?
Right. So far, what examples I've given are typically, at a point node or a fault zone or particular. But in a distributed power system, it's not just one or two circuit breakers. It could be multitudes of circuit breakers throughout the system protecting various circuits and sub-circuits. When that happens, though, it's good to have an intelligently networked system. So, for example, you could have an onboard microcontroller to do the diagnostic, sensing, and manage the communications. And there could be a communication network, be it Ethernet, LIN, CAN, serial, or Bluetooth. Depends on type of equipment and location, but could be multiple communication mediums to get the data to where it needs to be, mainly a control room, so actions could be taken.
Okay.
And all these actually, require an integrated network that's built around the silicon carbide switch itself. We do the actual hard switching, and there's a lot of control logic could be built around that to make it a safer and intelligent network system.
Right. So tell us a little bit more about that control circuitry. What else might we see in a system that uses one of these types of circuit breaker?
Okay, for example, a Microchip offers many of the system level components. We could talk about, for example, a microcontroller, like a digital signal controller, DSPIC type controller.
Yeah.
Or if you don't need the kind of performance of such single dual core processors, you can use a single 8 or 16-bit MCU,
Okay.
8 MCU 16 type controller. And that could potentially handle for example, the diagnostic on the solid state circuit breaker switch. It could handle potentially the PWM switching of when those, how to switch the silicon carbide MOSFETs, for example.
Right.
And on the other end, they could be communicating all the data back to the control room via a conduit that I mentioned earlier, any other various communication mediums. So there'll be like a network going throughout the ship with multiple subsystems of solid state circuit breakers that are, in a sense, linked to each other, and so they're aware of what's happening each part of that subsystem.
Okay. Thanks. Okay, so you mentioned silicon carbide MOSFETs now, so there's obviously power devices around this as well. Would you remind our viewers just what we offer there in that space?
Good point. So depending on your application, typically for these higher voltage, higher current applications beyond automotive, we offer a wide range of 700, 1200, 1.7 kV, 3.3 kV silicon carbide MOSFETs, diodes in both die, bare die, package, or module forms, and corresponding gate drivers, which is very important.
Yeah.
And beyond that, I mentioned a lot of the networking and control aspects of a solid-state circuit breaker. Microchip, for example, has DSPIC digital signal controllers, PIC8 or other MCU 8, MCU 16 microcontrollers for the control functions, a wealth of analog and peripherals that you would need, like voltage regulators, dropout, the small components that actually make the system tick.
Yeah.
And communication, whether wireless or wired communication, we offer a wide range of the protocols there, and a lot of other peripherals too. That's on our website that people can look up.
Okay. So if they wanted to get started on this or take a further look at these devices, how would they get started?
Best place for silicon carbide MOSFET, go to microchip.com/SiC for silicon carbide, and all the hardware, the software, the firmware, and all the support resources are there in different blocks that people can click through and easily access the data.
All right, awesome. Thank you so much for that overview, Jason.
All right,
At this
welcome.
point, let's go to Aaliyah and see if we have any questions from our viewers today.
Yes, we do. We have a question here from Ned coming from LinkedIn. What are possible certification paths for SSCB safety and quality for systems above 1000 VAC or 1500 VDC systems?
That's an excellent question because a lot of safety aspects related to solid-state circuit breaker actions. Now, Microchip at the silicon carbide switch itself does not necessarily, we don't put it through the certifications. We work with our partners or end customers to achieve the certification they need, and typically that might be The common ones like UL489 or 1557 where it talks about the molded casing with the power semiconductor switching inside and air gaps that's needed, all the safety and reliability issues. So we work with customers to address these issues and provide all the necessary silicon carbide rel data needed.
Awesome. Thanks, Jason. Second question here is coming from LinkedIn as well. This one is from Mahi. Can SiC MOSFETs be paralleled to achieve a higher current capability for SSCB applications?
Yes, absolutely. I mean, I mentioned that we have a range of 700 to 3.3 kV silicon carbide MOSFET devices. You can, depending on your system specification for the circuit breaker, you can parallel a number of devices and to achieve your current rating at the desired blocking voltage. And you pick your voltage and parallel them to meet your current requirements. And you go from there, whether it's discretes or picking the right die combination in modules to achieve the same output.
Great, thank you. Next question is from Varsha. They would like to know, in the event of a short circuit, how long can the SiC MOSFETs operate before failing?
That's a good question. Silicon carbide MOSFETs typically, if you're in the lower voltage range, 700 volt, 650, 700 volt range can withstand up to 10 microseconds. And the higher voltages are usually in the few microseconds, say 2, 3, maybe 4 microsecond range. That's typically enough time for the silicon carbide MOSFET to recover from the event.
Thank you. Next question is coming from Chicago. This one's from Jose. He's asking, why is solid-state circuit protection better than mechanical protection for DC circuits?
If you recall the first table I showed, we discussed there are a multitude of answers. It's obviously operating much more higher performance, switching at hundreds of microseconds versus millisecond range, so it's much faster. And there's no arcing involved, and there's no moving components for failure, mechanical failure, potential failures. So it's a power semiconductor switch, in a sense, that's very efficient. And also, there's more compact, rather, because you don't need all the bulky economizers and coils that's usually in a traditional relay, a mechanical relay, that you need to place on your system that could take up space and also heat up your system further.
That's great. Next question is from coming from Phoenix, from George. And it's, can the E-fuse be configured for bidirectional voltage blocking, and can it be used on AC circuits?
So the answer is yes and yes. In terms of the bidirectional application, you basically design in another switch of silicon carbide MOSFETs to provide the reverse or the bidirectional power flow, if you will. We call it omnidirectional power flow, because it could be to other multiple sources in either direction. And primarily, we talked about today protections for DC circuits, but circuit can be modified for AC as well.
Thanks, Jason. Next question is coming from Fatima, watching on LinkedIn. Which parameters are configurable, and what diagnostic capability does it have?
So we have what we call a TCC curve monitor that can be controlled on our circuit breaker, E-fuse circuit breaker solutions. And you can monitor basically, for example, the under voltage, the let-through current, the current trigger levels, let's see what else, temperature, and also the diagnostic of how the health of the E-fuse solution is running. All that can be communicated across different communication medium. Currently we have LIN because we have a e-mobility solution, but in the future Ethernet and other solutions are possible. You can communicate through those communication mediums to the control center that can, then the operator can use the HMI to take appropriate action.
Awesome, thank you. Let's do one more question. This one is from Santosh from India.
Oh.
Have you considered the impact of system parasitic inductances?
Yes, actually we have. We designed our E-fuse because the characteristics of silicon carbide that switches so fast. The energy buildup or let-through current is so low that there's no time. We don't allow the system time like a traditional relay to build up the inductance, and so that when it actually switches in a traditional relay, there could be that arc due to the inductance, the energy that's built up. The let-through energy is so low that in solid-state circuit breakers that when it switches, it switches and there's no fanfare about it. And you can reset it or do the appropriate actions and diagnostic on your system to find the fault and what's happening quickly without worrying about sparks and what have you.
Great. Thank you, Jason. Thank you for answering our audience questions. And for the audience, if you have additional comments or questions, you can email us at livestream@microchip.com after this broadcast. And don't forget to follow us on LinkedIn and subscribe to our YouTube channel. Back to you, Eric.
Thanks, Aaliyah. Jason, thank you again
Thank
for
you.
sharing your knowledge and expertise on this subject. Thank you to our viewers for taking some time out of your day to join us. Please visit us at microchip.com/coffee break. You can sign up for notifications on upcoming topics, peruse our library of previously recorded sessions. Our last episode for this season will be in 2 weeks. At the end of that session, we'll be sharing some news about the evolution and expansion of our live stream series here at Microchip. See you then.